things that we're going to look today is what are the things that you should take care when you're going to deploy a Kubernetes-based cluster, right? And why is HCD so important? And and what are the things that you need to take care to make sure that you have a very stable Kubernetes cluster? So those are the things that we would be covering in this particular session. So just about me. So my name is Ranjith Rajaram. I've been working with Red Hat with 16 years, and I actually do a lot of product support at Red Hat, and I've been a speaker at several conferences. I also own a media group known as Red Hat User Group. So I also an organizing member of the DEF CON India. I think that I'm going to cover today are, so we'll start with the basics, that is very short basics. And then we'll try to find what are the requirements that you need to keep in mind when you deploy an HCD cluster, and then how to capture the HCD metrics. So we will not talk about how to recover an HCD cluster, because that itself will take a lot of time. So I will, I will allow Humble to schedule a new session just to see like how you can recover a failed master node by using an HCD backup, right? So that is something for some other day, right? So any commands that I'm going to type, right? So all those commands are going to be on top of OpenShift. So now we are talking about Kubernetes, then what is OpenShift and what is OKD, right? So just wanted to quickly touch base on these points so that you would know like what is OpenShift first of all. So here in the slide you're seeing three set of icons. One which is on the left, which starts with Kubernetes, Docker, open container like this CI, OCI, right, which is on the left, and then on the middle you have OKD, and on the right you have OpenShift, right? So on the left you have individual projects like Kubernetes, then you have the Docker project, then you have the OCI, Open Container Initiative project, then the HCD, then the HA proxy, right? So if you want to deploy a Kubernetes cluster, and that cluster needs to be your container platform, so what you need to do is you have to first take the Kubernetes, the contents from the K8 project, then from the Docker, then from Manage IQ to manage your cluster, or even from HCD, etc. So you have to take all these components together, and then you have to stitch them so that so that you get a container platform. So in order to make your life easy, what this OKD project does is, OKD is again an open source project. You can still go and download and access them. So what this OKD aims to do is to make your life easy. So what OKD does is, it takes in all these projects and it gives you a pre-built container image. So the moment you download the OKD, it will have all the necessary components for you to start a full-fledged container platform, right? And then on the right, you are seeing OpenShift. So the OpenShift is again based on OKD. So all these, that is OKD, OpenShift. So the base is Kubernetes. So any command that is known to work on Kubernetes, they will also work with OKD project or with the Red Hat OpenShift container platform. The reason why I kept the slide here is because all the commands which I might type are basically on top of an OpenShift container platform. Just to avoid any confusion, OpenShift container platform is based on OKD. OKD is the upstream project or the open source project, and this OKD, the base or the core of the OKD is the Kubernetes, right? And before we go forward, right? So this is a very typical architecture of when you want to have a container platform which is going to be production ready. So this is how it would look like. So you have a control plane, and which is on the left. That is, you see, which are being marked as master, and then on the right you have the data plane, which is being marked as infrastructure node as well as the application node. So this is where your actual workload runs. So that is why we call it as the control plane. And on the left we have the control plane, and on the right we have the data plane, right? So here, if you see, I have shown you three master nodes. So you're going to have, so when I say control plane, you're going to have three or more right? So if you just keep as one master node, then there's a high chance of single point of failure. So if the master node goes down, then what would happen is the workloads will run, but you will not be able to add a new pod, or the pods can't do and a scaling, right? So those things won't happen. But whatever is being running, it will run, right? So that's the reason why we actually have shown you at least to have three master nodes. And today in this session, what we're going to look at is the data store that you see with the orange box. So data store is nothing but HCD. Okay, so now we're going to look at the very basics of HCD, and I will only touch upon a few things which will help you to understand why you need to have a stable HCD cluster, which would help you to have a stable Kubernetes cluster, right? So everything is linked to HCD's performance. So HCD is a distributed key value store that provides a reliable way to store your data across a cluster of machines, right? So if it is a single cluster, if it is a single node, it is easy. So whatever you write, it has to just save it on a single node. But when you have multiple nodes with the same data store, so you have to make sure that whatever you write in one store is also being written in all other nodes, right? So HCD make sure that you have that, it also provides you the way how you can do it. And it actually masks masks those things from you. You need not do anything much further, right? You just have to start HCD in a proper way. And then why is HCD so important is because it is the core database of Kubernetes cluster. Every object, every operation, and it's just not the object, state of the object is everything is stored in the HCD database. So if the HCD database is down, you would not be able to go and retrieve the state of your container or your pod. Like whether the pod was running, whether the pod was down. If the HCD is slow, any commands that you try to retrieve them, that is like kubectl get pods or kubectl get logs, or not logs, get pods, get projects, get config map, get secrets, everything will be hung, right? It will not run. And if there's a lot of delay, in case if you're going to do some sort of external components are going to talk to your API server, right? If the HCD is not working well, your API server will get affected. That will affect your cluster. And then HCD is written in Go, which is written in Golang. It uses a Raft protocol for distributed consensus. Okay, so we will take a look at two of the major operations that happen with HCD, which is known as the log replication and leader election. So why this leader election? Because you have, I've shown you, right, that is you need to have three master nodes, and all the three master nodes will have its own data. So they all run in a separate, on separate nodes, right? So just to maintain the integrity and the consistency of the data, one of the node has to be the leader. So we will take a look at what is this leader election, right? So now we'll just go to the to a different website, which kinds of which kinds of help us to understand the Raft protocol, the basics of the Raft protocol in a better way. So when you start an HCD process, the node or the HCD server can be in one of the three states. It can be a follower state. It can be in a follower state. It can be in a candidate state. Okay, so as I said before, a node can be in either one of these following states. That is, it can be in a follower state. It can be in a candidate state, or it can be a leader, right? Let's skip this. Yeah. So since I had to restart my Firefox. Okay, so let's look at this, right? So now Raft is a protocol for implementing the distributed consensus. The reason why we are going to take a look at the Raft protocol, the very basics of the Raft protocol, is to help you understand why you need to configure HCD in a proper way, right? So yeah, so let's skip this. So as I said before, so now once a node starts, right? So let's assume that you're going to start your Kubernetes cluster, right? So each node when it starts, it will be in a follower state. Okay. And then it will just, so all the nodes are in follower state. So it is not, it doesn't get any message saying that I am the leader. So the moment it doesn't get any message as leader. So these timeouts are actually in very small milliseconds, okay? Like 100 milliseconds or 150 milliseconds. So, it's just than a second, like 150 milliseconds. So, within that period, if it doesn't hear, someone saying, I am the leader. So what happens is at that particular point, the first node which started in the follower state, there's a timeout that happens. So the moment it doesn't hear from the other node saying that that there are no leaders, then what will happen is that one of the node will start to assume that it is the leader, and it talks to the other node saying that, no, I am the leader. Do you agree? Right. So what it does is it sends some oaths to the other nodes, right? And the nodes will reply with the oath. So the moment one of the node, right, becomes so first it will be in a follower state. So the moment it finds that there are no leaders, it will go into a candidate state. Then at this particular time, it will do a leader election, and that particular point of time, if it gets the votes from the other node, it becomes a leader, right? So now here in the website, you can see the leader is being marked with a black circle, right? So now thing so now this is the most important point. Any change to the HTTP database has to go now via the leader. Okay. Any change to the HTTP cluster has to go via the database. Other nodes can still give replies to a read request, right? If it just to read something, the other nodes will reply back. But if there's any change, that is any write request that comes in, that has to go via the leader, right? In case if a write request goes to a node which is not the leader, then that the other node will read direct those requests to the leader. Okay. So now let's assume that you have a client, right? So the client now talks to the leader and says, okay, set 5. Okay. It says that, okay, this is a key, set the value of key as 5. Okay. Now let's see what is going to happen. Right? So now the leader has got a write request. Now what it is going to do. Okay. Now each change. So the moment a client says, okay, change this value to 5 or add this value to 5, what it does is it doesn't save to the store. It will keep it in a log known as no, just for the moment it's a log, right? It will keep it in the log. It will not write to the disk. Okay. And now what it does, right? Now the node, what it does is the master node, what it does is whatever was the change request, it sends to the other nodes which are in the follower state. Okay? It will send those requests, right? So now you have to keep in mind the client is still waiting. The client doesn't know if the request has reached which has reached the leader node, and leader at this time what is doing, it is just saving those requests in a log, and then it is sending those write requests to other nodes. Now the other nodes, they need to write the data, right, and reply back. So now the thing is, all of the nodes have all the nodes now has the value data 5, right? It again notifies the other nodes that this change has been committed. Only after this is what, then after this the leader will reply back to the client, right? So any request that comes from the client, it goes to the leader. Leader has to send that data to the other nodes. The other nodes have to commit those entries, and then it gives you a reply. So now it is easy to guess, right? If you have a very slow disk, right, any write request will come, it will be delayed, because the write request has to be committed by 3 of the servers before it will reply back to the client, because all these HCD, the system call that it uses is fsync. So the fsync system call, what it means is that before replying back to the client, it will make sure that whatever is the right request that is returned to the disk, and then only it will reply back. So here, it is just not one node, all the other nodes as well, right? So if one of the node is slow, and it will have a major impact. And then the other point is the network between the nodes, right? So if you have three HCD nodes, and if they are on an very if they are very distant enough, each write request will have its own latency due to the network. So what you need to make sure that even the network between these nodes has to be stable, right? So if there's any delay, if there are any packet drops, you're done, right? Your HCD will have to resend the packet. It will have to wait for some time. There's a lot of corrections which needs to happen. So keep in mind is that from this process, any change, any write change that happens, it has to be committed on three of the nodes before it will reply back to the client. Okay. Okay. And I hope it is clear now, right? Why these two operation of HCD. Now let's look at how the Kubernetes is going to use HCD, right? So any request, though, let's say for example, you have a you have a developer, right? And the developer wants to start a pod. So what it does is it talks to the API server, right? So now the API server, before even it can allow a developer to create a pod, it checks the HCD for the rollback access control. It just verifies that. So if the developer is allowed to create, then the API server will allow, right? So that is where the first step. So any commands that you execute using kubectl, right? It goes to an API server. The API server verifies it with the HCD, right? Now here we're going to take a look at a developer who's going to create a pod. Now let's assume that the developer has the required privileges to create a pod. So the moment the API server allows it, the pod, the details of the pod, like name, which namespace, how much resources, all these are being saved on the HCD server. And this scheduler, right? The moment it keeps a watch. So the moment it detects that there's a change, a new request has come, it picks up the data from the HCD via the API server, and it says, okay, based on these so and so request, you can start this pod on this particular worker node. Now again, the kubelet will detect that. It will talk to the API server. It will go and check, and it finds that okay, there's a request to start a pod. It goes, it starts a pod either using Docker or Cryo. So it starts a pod, and again, the state of the object, right? Whether it just started, whether it just failed, all these things are again have to be saved on the HCD, right? So now here, I think I'm sure that now you should have a better idea why HCD is so important for the stable Kubernetes cluster. Everything, so all the requests, like even from the other components, like an operator, from an external components like a CI/CD pipeline and things like that. So everything will talk to the API server, from API server to the HCD, and then all the magics happen, right? So HCD is the most critical component of your Kubernetes cluster. Right? Now let's look at the HCD system requirements. So if you're going to deploy a Kubernetes cluster, it is always good to have the master components, that is, at least 3, 5, or 7, or 9, right? So the number of master nodes has to be in an odd number format. This is because it will help you to tolerate more node failures. If you have 4 node cluster, you can only tolerate the failure of one node. If it's 5 node cluster, you can tolerate the failure of 2 nodes. So if you have an HCD cluster of 3 nodes, it can tolerate a failure of one node. So during this failure, quorum is still maintained, right? It will allow you to make write requests, that is changes to the database. It will also allow you to read, right? So now up to this is fine. So if you have a three node cluster, if one of the node is down, you still have two more nodes, and during this phase, your cluster will be working in a proper way. Only when you in a three node cluster, if two of the master nodes are down or two of the ETCD server processes are down, then that is this phase when the column is lost. And this particular phase, HCD will block all write requests. You might be able to read, but it will be on a block state, right? I mean, any new changes, or if you want to scale your pod, everything will be in a block state. Right? So you have to make sure that you deploy at least more than one master node. So when I say master node, a master node with all the control plane components like the API servers, scheduler, controller manager, right? So those sort of things has to run in more than one node. So if you're and in case if you're going to deploy Kubernetes cluster, you still have the option to run HCD on a separate nodes, right? So that will also allow you to give maximum resources to the HCD processes. In case if you're going to run all the master components, including the HCD on the same node, then you have to make sure that you don't run any workload pods on top of those master nodes. And then the master node also needs to have enough compute resources. In very plain words, for HCD, you need to have a fast storage, right? If possible, right, always use a SSD or an NVMe disk to back your storage. So if you go to a cloud provider, that's something that we'll look later. And then, as I said before, why the store? I mean, why you need to have a faster storage? Because any write request comes, it has to be saved very quickly, and then only it will reply back to the client. So if the client keeps on waiting for more than a minute due to the drops in the network, due to slow disk, your client will say there's a timeout and it will exit, right? And then you might have again it will have to retry, and again if the disk storage will have a problem, right? So again, the network should be, the latency in a network should be under 2 ms. That's the maximum, and there shouldn't be any drops. If you're running in a virtual platform, make sure that there is no CPU overcommitment. Right. Now, again, this is just for the virtual platform. Try not to share the same disk storage or the LAN, right? So let's say, for example, if you have multiple virtual machines and if they are all sharing the same storage or the LAN, there's a high chance that if there's a high IO coming from one of the virtual machines, like a like from a worker node, it might, the more IO coming from one node can affect the other virtual machines. So you could actually still reserve, play with some C groups, and you can make sure that your HCD will always get the more number of IOPS. But it is instead of going into those lines, it is better to make it simple. That is, don't share the LAN. So I mean, have a dedicated LAN for your master nodes. So when you're going to deploy a Kubernetes cluster on a cloud platform, always look for if they have advertised the potential IOPS number. So mostly the cloud platform vendors would advertise the random or the concurrent IOPS, because those values are always higher. Right? The higher the values doesn't mean that you will get a better performance. The variations, there can be a lot of variations due to certain factors. So now the first thing is that always look for sequential IOPS. So this information is already available in the upstream HCD documentation, where they say, so let's look at the disk. So here, right, if you, I'll just make it big. So they talk about a lot of things like what should be your IOPS and all, right? Like, whether whether you might be okay to have with the 50 sequential IOPS. So I mean, those are all good, but at the end of the day, if you need to have a stable cluster, it's always good to back your HDD storage with an triple SD, sorry, not triple SD, just SSD disk, or with an NVMe disk, right? So, and if you're going to deploy it on a cloud platform, always choose for disks which are being backed up by SSD disk. So I mean, those are known as the provisioned IOPS, right? Okay. Okay. So now let's assume that you have a Kubernetes cluster, and you have to check whether the cluster what you have is working well. Right? So now you have to make use of some HCD metrics. So before going to the metrics sort of stuff, let's look at some of the logs. Right? So the HCD logs has a ton load of information that will help you to understand whether your HCD cluster, that is a 3-node HCD cluster, is working well as per the ideal timings, right? So as I said before, everything with HCD is in milliseconds, like 10 milliseconds, 100 milliseconds, right? So now what this HCD does is, for let's say, for example, you're going to do a write operation. If the write operation is going to take more than 100 ms, it will log a warning. Okay. So now one warning might be fine, two warnings might be fine, but for any write request that comes to an HCD database at that particular point of time, you're seeing a lot of warnings saying that the write is taking more time, then that is something you need to worry about. On an ideal cluster, a cluster which is working well, you should not see any of those warnings. Okay. So now let's look at some of the operations what the HCD does to make sure that the HCD itself works, in a more ideal way. So that process is known as compaction. Okay. So what it does is, now let's take a look at how what is this compaction and what it does, right? Now let's say we actually told you, right, the HCD is a key value data store. Now what does it mean? What does it mean by key value? So what it means here is that the key is the name, okay, key, and the key has a value range 3. So now whenever I want to check what is the data store, I check by using the key, right? So now what I'm going to do is I'm just going to add a value to a key which is named as name, right? So now this has been saved in the HCD database. Now, if you want to um, retrieve the value, right? So it has retrieved the value that you said, which is 23, right? So now, so let's say, for example, you have a pod, all right, and the state of the pod, changed from started, error, failed, crash back loop, right? So there are many states that could go through. I mean, based on the error, but it is basically started, stopped, and exited, right? So those are, so for the same key name, you could have different states, right? For example, now you're going to change the value of scope, right? Now it's 5. So for the name, for the same name, so the name is the key. For the same key, I'm changing and updating the value. right? So now what I mean, what I've shown you is, right. I made a lot of changes, right? Like, eight. So now what I'm going to show you is that the HCD maintains the history or the revision of changes to a particular object or to a particular key, which is the name, right? So it will keep on saving those changes. I mean, why this is being done is because in case if you have an application just wants to read what was the previous value before the change, it can go and check the previous version, right? So that is why the HCD keeps track of all the changes, all the revisions that happen to a particular object. So now what would happen, right? Your cluster, the size of your cluster database can keep on growing, larger and larger. So the larger a database, slower is the performance. So now to avoid it, what the HCD itself does is it goes and does the compaction, and it will try to clear out all the previous revisions at a set interval. And so now this operation is very, very important, because when this compaction happens, the HCD database goes into a block state. At this particular point of time, it will try to, delete, remove, make a lot of changes to the HCD data store. So if your data store is slow, it will throw you a warning. If it throws a warning, then what it means is that it is in a block state. It will not allow you to make any new write requests. And if it is the leader, if it spends a lot of time in a block state, it can cause some trouble for you. So in the logs you would see such warnings, that is, MVCC finish schedule compaction at, it says that at so and so, that is the epoch time, and within the bracket it says it took more than 100 seconds, that is the 100 milliseconds, which is 112. So it is slightly higher, but it is still a warning, which might, these are the things that you have to go and take care. It is slightly above 100, so the ideal value is to be below 100. If it is above 100, it will print a warning. So one warning, it is slightly above warning, is okay, but you should go and check why this warning is coming. And then you would see one more line where I mentioned that compaction itself took 3 minutes. So for 3 minutes, that HCD server process was in a block state. If it is in a block state, it will not respond to any other operations that should happen with HCD. So let's say, example, if it is a leader that is getting stuck, no new write request will come in. And if the other node doesn't get a heartbeat signal within, let's say, within 150 ms, it will start a new leader election, right? So your cluster database would go, the state of your cluster database would be in a very weird state, which can really affect the performance. So these are there in the HCD logs, right? Now the other warning is that you would see in the logs is server is likely overloaded. So in case if you don't have enough CPU resources to perform any sort of an IO, any sort of a network IO, it will bring this warning, right? So if you see this happening, then what you do is you go and check the CPU usage, whether the HCD has enough CPU resources or not. If you have enough resources, then it points to a disk issue or to a network, right? Now this is the most, one more very important log messages that you need to keep in mind. Apply enrich to blocks too long. So what it means, right? So as I said before, a write request comes to the leader. That request is not committed to disk. It is saved in the log, and then that log is being replicated to other nodes. The other nodes have to commit, and then it will send the reply back, and then only the leader will come, right? So there's a lot of process that happens. Now, in case if you see such a message, what it means is that there is some sort of a delay in the disk commit, either in one of the nodes, right? So if you see it on the master, it could be a problem on the other node. So you should have to check the logs of the other nodes as well. If you see it on the master, then it is very clear the master node is slow. So the warning actually happens when you cross 100 milliseconds. Most of the cloud platform, what I've seen is it is kind of at close to 50 milliseconds. But if you're going to use like an NVMe on a, yes, just in this, it can, the write can just happen within 5 ms. So you are actually safe. So just once again, if it is an ideal cluster, if your cluster is working very well, you wouldn't see such sort of a warning message, right? Now, this is also very important, like fail to send heartbeat on time. So this is again a warning, right? If a leader is not able to send a heartbeat on time, the other node, what happens to the other node? It will say that the master is down, and it will start an election process. So during this election process, there are no leaders. As I said before, if there are no leaders, the write request won't be happening. Right. So this is a trouble. So you have to make sure that so this is one of the warnings that you should catch on time. If there are more, if you see that the leadership change is happening more often, right? So then what it means is that there is a lot of trouble on your HCD cluster which needs some attention. Then the other important part is the clock on the HCD nodes should be in sync. So make sure that the nodes have a clock source which is very reliable. Okay. So now let's look at some health check commands. Right. Okay. So I've just run a command where it says the health of which gives you a good idea of the state of the cluster, not the health, the state. So as I said before, a node can be in a leader state, in a follower state, or in a follower state, in a candidate state, or as a leader state. So now when you type this command, what you're seeing is that you have 3 HCD nodes, and one of the node at the bottom is the leader, and then what you're seeing is the DB size. Okay, now your HCD DB size is close to 250 MB, which is fine. And this, so there is no, I mean, we can't really say that, okay, this size is good, this size is bad. You could have a 1 GB or 4 GB of your HCD database size, but just make sure that you have a faster disk. So you can really tell, but the smaller the DB size, it's always better. Okay. So now, you are seeing the version of HCD as well as the DB size, right? And also whether a particular node is the leader, or whether which node is the leader. That is what you find out from this particular command output. Okay, let's go to the other part, which is it is just to check the health of the cluster. So now you might see the values healthy. It doesn't mean that it is all good. You should still go and check the log. So here the output says that things are all good. But the thing is that you still have to check the logs to verify if you're seeing any of those warning messages that we saw. Right. So these are the few commands that you type and check what the status of the HCD cluster. So you could run some sort of script where it keeps on checking this. So if your cluster is not healthy, if one of the members is down, you would see such, and so you would see the reply as unhealthy. Okay. Okay, so now we check the logs to verify if the if the state of your HCD cluster is in a proper state or not. So now the next phase is we are going to look at the metrics. So HCD also, sends out the metrics. You can use a curl command, like a curl command. You can query the HCD server process and get the metrics. So when you get the metrics, you have to make sure that you get the metrics from all the 3 nodes. Now let's say, for example, in case if you don't have a GUI or a dashboard or a monitoring dashboard like Prometheus, you can still use command line options to retrieve the metrics of HCD. So if you're going to do the command line, you have to do some sort of manual calculation to find the 99th percentile for each of those outputs. As I said before, HCD uses fsync to write data to the disk. So you have to check that particular value of the fsync, that how much time it is taking for each of the write operations. So what we do is not for each. So we will not go and measure for each and every fsync. We'll take the 99th percentile of this particular variable, which is the fsync, and we'll see if it is well below 10 ms or let's say like 20 ms, right? If it is well below the ideal values, then we can say it is all good. Right? And one more thing is that we also have tools to which you can check whether whether the disk is performing well. As I said before, there can be a lot of variations that can happen due to several factors. Let's say, for example, you have an HCD cluster which is running as a virtual machine. And in case if you're going to take a snapshot of the virtual machine at that particular point of time, even if you have a hard disk, a faster disk, you might see a little bit of a pause or a glitch that might happen, right? So even if you're faster disk, so you actually check with FIO and you see that the disk is fast, but still you see a lot of warning message. So now you have to go back and check several things to verify that why is your disk slow. Okay. So now these are the most important HCD metrics that you need to keep track. If you have a monitoring dashboard like from Prometheus, it can query HCD and it can get those values for you, and it will show you in a nice GUI chart. Right. So if you don't have the dashboard, you can retrieve them still using command line, and you can go to that particular log file that the metric stats, and you can do some sort of a manual calculation. Doing that manual calculation is outside of the scope for this particular session because it takes a lot of time. So now the ideal values that you see is on the extreme right. So for any backend commit, the duration should be less than 25 ms. So we are not talking about seconds, we are talking about milliseconds. And for the fsync, it has to be less than 10 ms. 10 ms or less than 10 ms. The peer round trips at the network level should be below 50 ms. CPU IO rate should be less than 4, right? So these are the ones that you see on the top are the ones which are known as the most important metrics. The one you see at the bottom still has to be verified, but it is optional. If now, as I said before, the leadership change that happens within the HCD cluster is very important. If you see more and more leadership changes happening, then it means that there is some sort of an issue which needs to be corrected. Right. So we saw something known as the compaction. The compaction model does this. It removes the older revisions, and so when it does that, what will happen is it will just be removed, but HCD won't be able to use that space. So the DB size will still be, let's say, 1 GB, which is being shown, but the actual usage might be very less because the compaction has happened and it has removed. So at this particular point of time, you would see 2 different values. So if you see that HCD MBCC DB total size in bytes, and then you have one more value which says what is the actual in use, right? So if you see a 50% difference, what you need to do is you need to run a defragment of the HCD database to release those deleted files from the ETCD space so that they can still be used. Right. Now we will quickly look at the graphs, how you can find out whether your ETCD disk is working well. So most of us prefer to look at a dashboard, look at the metrics in a dashboard, and quickly verify if it is all working well. Okay. Now this is just a screenshot from the Openshift container platform dashboard, where we're going to show you the fsync. So we're just going to see if your ETCD is working well from an fsync variable, right? So as I said before, it has to be 10 or below 10. So here, if you see, so this shows that the value is slightly above 10 ms, that is 0.04 seconds, which is 40 ms, slightly above, right? So when I say slightly above, it is above. So you have to go and check why this is happening. It has to be below 10 ms for a proper ETCD working cluster. All right, so you could use these queries, right, on your Openshift or on your Prometheus dashboard. You can run these queries and you can find out if you're well below these set values. Right? So the first one, we are going to check whether are there any values which have we are going to check whether at any particular point of time whether this fsync value the fsync write has gone above 20 ms, right? So the value that we are trying to say is that if it is above 50, okay. Let's take a quick look at the output itself. Right? You will try to understand that. Okay, so we will get back to it. Wait. Yeah, so this is a dashboard of the Openshift cluster. It is in the VPN. So okay. What happened? Let's wait. After we'll take a look at it a bit later. We'll allow it to load. Okay, it's come. Okay. Okay. No luck. Let's take a look at it at the end. It's like okay. So the first graph, right? So we're going to see two queries, the output. So we're going to run two queries, which is going to check, if the fsync due to duration, the 99 percentile of the fsync duration was above 20 ms or below. I mean, what's the status? So now what we're seeing here is that this is a cluster which is working very well. Okay, most of the 99 percentile is close to 8 ms, right? And only for one node, it slightly went close to 10 ms, right? But for the rest of the nodes, it was all good. Now, this is the second query. We expect an EMT graph because we are trying to check if there are any percentile values which are above 15 ms. So if it is an ideally working cluster, this has to be empty. If it is not empty, you would see some graphs, some spikes happening. Okay. Now this is a screenshot from a cluster which is not really working well, right? Here you are seeing that it is taking 400 ms. If it is taking 400 ms, means there is something really a problem which you need to solve, right? Now the question is, how can you improve your ETCD performance? Let's assume that you saw some warnings, Now you have seen some timeout happening when you type the kubectl get pods. It is taking a lot of time to get the reply, or sometimes it is going into an timeout state, right? So now, how do you improve the performance? So these are some tips, right? So you could, if you are using a shared storage, try not to use a shared storage. Use a dedicated LAN. Use a faster disk, which is being backed by SSD disk or NVMe disk, right? As I said before, if there's a huge difference between the sizes, that is the actual size in use and the actual size which is being listed, you actually need to run a deep fragmentation so that those spaces are released. So the compaction will only remove the entries, but it doesn't clear out the file system space. So you need to run this defragmentation at the ETCD level, which actually helps you to reduce your file system usage, which will actually improve your DB performance, right? Now, this is also very important, right? So there could be some projects which actually does a lot of, it saves a lot of things like secrets, config maps, the certificates. It saves a lot of things to the HCD. So which should actually, and what would really happen is your HCD DB size will go higher now. You can check these things, that is to see if a particular namespace is consuming more of your HCD space, or if there's any CRD, which is actually CRD means custom resource definitions. So if you have an operator in your cluster, it will make use of this CRDs, right? And it can also abuse the HCD database by storing a lot of information. So if it is a properly working CRD, it will not store a lot of data. It will only store what is really needed, right? And then, if you're doing a lot of backups of the virtual machine or snaps of the virtual machines, try to avoid it, and just concentrate of taking the backups of your HCD database, right? Because you can always recover your master node. If you have 3 master nodes, if one of it goes down, you can always safely recover them. You need not go and take a look at the snapshot, because when you try to recover from the snapshot, it will have the older contents within the HCD database, and that will lead to a lot of problems, right? So better take the HCD DB backup. That's more than enough for you to recover. As I said before, how to recover your HCD cluster or your master node, that's a very different topic. That's something which I can do at a later point, right? So now when you connect all the dots, right, to verify if your HCD is working well, you check the logs, um, um, you check the HCD metrics. Then on the node, you check whether there are any hardware faults. You check for any packet drops using IP-S command. Then use the curl command to check whether the API server is responding quickly. If the HCD is slow, the API server will affect it. If the API server is affected, every functionality of a cluster will be affected. And then you check the number of objects which is being stored on the HCD cluster. Now, this is an example, right? The IP-S link command, it shows some drops here. Okay. If you see a drop, it doesn't mean, it is something really bad. The moment you see 1 drop, 2 drop, 3 drop, right? If the drops are close to 5% of the total packets that the machine has processed, then it is a problem, right? So you can do a simple curl command to the API server, and if the response is being received within let's say within a timeout of 2 ms, it is all good. If it is slightly close to 6 to 8 ms, that means there's slightly some sort of an issue, or some sort of a networking issue, some sort of storage issue. It's not able to quickly read the data from the HCD, right? These are the things. So this is a very simple check, right? Is incurred. So now, to check whether your disk is working well, or before even you deploy your Kubernetes cluster, you have to verify if your HCD, the storage for the HCD is working well. You have some suits like the FIO soup, right, where you can run them. You also have this HCD perf soup. So this is just one of the projects by one of my colleagues, where it kind of shows you some of the values which actually tells you whether your disk storage is good. So just to make it very easy, at the bottom part, right, at the bottom of, so if you see on the right, right, there is a line which says bad, 99 fsync is higher than 10 ms. Right. So now that FIO, to make it easy for you, also shares its observation to you that whether the disk is good or not. Okay. So it will give you a line like that, whether the fsync is within the 10 ms or not. So even if you see if it is like 12 ms, 13 ms, it might be good, but if you see it's about 10 ms, then that means there's a high chance that things might go wrong. As I said before, one warning message, two warning message doesn't mean it's a problem, but it's a sign that the performance of the ETCD can get affected in the future when the DB size goes high, or when there's a lot of variations that happen in your cluster environment, right? So this is a very simple command how you can go and check the number of keys, right? Let's say, for example, so when you run that command, this is the output that you get, right? If you add all those values and if the number of keys, above 8,000, in some of my experience, that has shown us that the performance of the ETCD can get affected. Let's say, for example, if you're running on a disk which is of 7,200 RPM and it gives you 56 sequential IOPS, during that particular point of time, if these sort of data, if the number of keys are slightly above 8K, your ETCD database can get affected. Yeah, right. Backup ETCD, it's very important. As I said before, don't think about taking a backup of your master node. Always think about taking the backup of the ETCD database. If you just take the backup of your master node, the content which is stored in the ETCD database can be old, right? It can have the older values, right? Then it is very difficult to see. So take the database of your ETCD, and the backup should be taken during off business hours so that it doesn't affect. Right. So the best practice, this is the last slide. Use a faster disk always. Make sure that the CPU has enough CPU and RAM. So for typical ETCD cluster, it is okay to have 8 GB, but if you have more watches and more data to be stored, go for higher RAM. So always check the process size, your DB size, and keep them on track. That is, keep it in a minimum. And from a networking perspective, make sure that there are no drops. If you're going to have ETCD clusters distributed across your data center, make sure that the round trip is less than 2 ms. So make sure that your other data centers is close to your current data center, right? And then also make sure that the total consumption of the keys are kindly close to 8K. Right. Yeah. So if you have any questions, you can ask me now, or you can ask at the end after the next session. Humble, do we have any questions on the chat?
Yeah, we did have one, which is about the system call when you mentioned about the operations on ETCD, but I have already answered that. It's the system call.
Okay. Okay, great.
Yeah.
Okay.
I don't see any other questions. Right. I don't see anything else on the chat room. But if anyone has any question, maybe 1 or 2 questions, we can take it now. If you can raise your hand, I can unmute, or you can unmute yourself.
Yeah. So if you don't have question, it is like you understood everything I said, or maybe you did not follow it.
It was very insightful session, Ranjith. Really detailed one, a great one, as always. So let's stop recording.
I have a question.
Okay.
He was mentioning multiple times about the defragmentation of ETC DB storage, right? But on the modern file systems, defragmentation is not relevant anymore, right? So I'm just trying to see what.
Yeah, so this is very specific to HCD, right? It's not about the modern file system. It is very specific to HCD. So when a compaction happens, that is when the previous revisions or the changes to a key is being removed, right? The space on the file system is not removed, right? So the compaction, so this is very specific to HCD, right? It is not due to a file system feature or whether it's about the modern file system. So the HCD audit does this, it just removes the data. That doesn't mean that it has cleared the file system space, right? Only when you do an defragmentation at the HCD level, okay, not at the file system level, at the HCD level, only then that space is being cleared from the file system. Okay,
Yeah.
I hope that has answered
Yeah,
your question.
it's actually the database storage structure, not the file system level writing.
Yeah, right, exactly. Yeah. Okay, guys. So I think I think it's time for the second session from Sejit sir. For the moment, I think there are no further questions. And if you still have a question, you can post them on the Meetup page. And even you still have an option to ask that question at the end of Sejit sir's session. And yeah, thanks, Amber. I will just wait.
Once again, thanks a lot, Ranjith. Very detailed session and a great one. And thanks all.